All right, here's the video for note 7-1, which is Introduction to Sampling Methods. So since there's a sub today, I'm just going to go over a couple of announcements. So number one, Unit 6 tests have been graded. The grades have been updated. The casino products were also graded, so make sure you take a look at Aries and see how you did. Turn in any missing assignments from Unit 6. In particular, your stamp sheet and practice tests that was due on Friday. If you haven't turned those in, turn those in ASAP. For every day that it's late, you are losing points, and that was a decent chunk of points that you are missing if you didn't turn those in. So please get those in as soon as possible. All right, so for today's notes, you're going to be taking them on pages 71 to 72. I'll give you a stamp sheet tomorrow. There are quite a few notes that you are going to be taking directly in your notebook. It's a lot of definitions, but please try and listen and understand as much as possible in this video. And any remaining questions that you might have about whatever was in this video, we can go over tomorrow. So first, let's start off with the difference between parameter and a statistic. So parameter is a number that describes a population. So parameter, population. Usually this number is unknown, and it's usually what we're trying to estimate. The symbols we use for parameters are usually Greek letters. So for example, we use the symbol mu for the population mean, and we say that mu. We use the symbol sigma for the population standard deviation, and that symbol is, you would say it as sigma. And then we use p for the population proportion. So these symbols we use to describe the population, these are all parameters. So for example, if we take the average household income of all individuals in the US, that's considered a parameter because it's describing the population, all individuals in the United States. A statistic is a number that is computed from the sample. Okay, because we are computing this number, it is observed and known. We use a statistic to estimate a parameter. So since parameters are usually unknown, we use statistics to estimate them. The symbols we use for statistics are usually regular letters. So for example, we use the symbol x bar for the sample mean. We use S for the sample standard deviation, and then we use p hat for the sample proportion. So these symbols we would use to describe the sample. These are all statistics. So for example, the average household income of a sampled group of individuals in the US would be considered a statistic. So that average x bar would be a statistic. All right, so let's take a look at an example here. It says at a particular college, 78% of all students are receiving some kind of financial aid. The school newspaper selects a random sample of 100 students, and 72% of the respondents say they are receiving some sort of financial aid. So first, let's identify what is the population and what is the sample. Well, the population is kind of everyone who we're talking about. So in particular, we're talking about all students at a particular college. So maybe we'll just say students at the college. And our sample is the random sample of 100 students. So sample of 100 students. All right. So now we need to identify what is a parameter and what is a statistic. Well, since these are percentages, we know we're going to be using p and p hat. So we use p for the parameter and p hat for the statistic. So the parameter, we need to figure out which number is describing the population. Well, this says 78% of all students, which means that 78% is a parameter. So that's going to be p equals 0.78. For p hat, this says 72% of the respondents, meaning the respondents of this 100 students. So in that case, that's the describing the sample, that's going to be p hat. So that's going to be 0.72. All right, so pause the video. I want you to try to see if you can answer these questions on your own. These don't need to go in your notebook. You can do it with a whiteboard pen. You can do it on scratch paper. You can just think about the answers. But pause the video, read this one, and then when you think you're ready to check your answer, play the video, and then I'll go over it. So this says a nutritionist wants to estimate the mean amount of sodium consumed by children under the age of 10. From a random sample of 75 children under the age of 10, the nutritionist obtains a sample mean of 2,993 milligrams of sodium consumed. Okay, so what is the population? So in this case, we're looking at children under the age of 10. Okay, and our sample is who we're actually collecting the data from. So it says a random sample of 75 children. So we'll say the 75 children. And then it's asking if this underlying number is a parameter or a statistic. So we have to see, what is this describing? 2,993 milligrams is the sample mean. So since that's a sample mean, that means it's going to be a statistic. The reason we know it's a statistic, it's because the number is describing the sample and not the population. All right, here's another example. It says the Gallup poll. Actually, I think this is out of order. Is it? Oh, no, this is right. The Gallup poll asked a random sample of 515 U.S. adults whether they believed in ghosts. Of the respondents, 160 said yes. Is this a parameter or a statistic? Why? So in this problem, what we're calculating, it's a proportion. This is going to be a statistic, right? Because this number is computed from a random sample. So this is considered a statistic because it's based off of a sample. So it says calculate the proportion of individuals who say they believe in ghosts. Well, since it's a statistic, we're going to use p hat. It's a sample proportion. And to calculate the proportion who believe in ghosts, it's going to be 160 divided by 515. So 160 divided by 515. That p hat is going to be, we'll say 0.3107. So that's the sample proportion. All right, so the question is, does a statistic equal a parameter? Okay, the answer to that is no. A statistic is an estimate of the parameter. So for example, if we took another sample of 515 US adults and asked them if they believe in ghosts, you're probably going to get a different p hat, right? It's not always going to be 0.3107. It might be around 0.3107. We can maybe say about 30% of US adults believe in ghosts, but if we take a bunch of samples and calculate the proportion who believe in ghosts, it's going to vary. It's going to be around 0.3107, most likely, but it is going to vary. So that's called sampling variability. The value of a statistic varies when we have repeated random sampling. So we take a sample, calculate a p hat. It's not going to be the same every time. Well, if we took all of those p hats and we put them on a graph, right? We made like a dot plot. This would create what's called a sampling distribution. Sampling distribution is a distribution of values of the statistic in all possible samples of size n from the population. So this would be of size 515. So again, if we just took over and over and over again, a sample of 550, calculated a p hat, graphed it, took another sample of 50, calculated a p hat, and graphed it, over and over and over again, we'd end up with some type of maybe distribution that we can use to estimate the true proportion of adults who believe in ghosts. Okay, so now you're going to pause the video. You're going to do the activity on the handout you got in class. You can also eat your Reese's Pieces during this activity since it involves Reese's Pieces. You are going to be turning in this worksheet at the end of class. When you are done, come back to this video and make sure you watch the rest. Okay, so in the activity, I'm just going to go over instructions real quick. This is what the activity should look like. You're going to type in this website into your computer. And it's a simulation website. So you need to make sure, before you run your simulation, make sure that your settings match the ones in this photo below. So the probability of orange should be 0.5, number of candy should be 25, number of samples is 1. You want to uncheck the show animation button, just because if you keep it checked, it's going to take forever. You need to make sure you're calculating the proportion of orange, not the number of orange. And then you want to make sure the summary statistics thing is checked. So then what you're going to do is you're going to go through the instructions here, answer these questions, and then when you're done, when you get to question number 10, you're going to come back to this video and continue the notes. So go ahead and pause the video, do the activity, the handout you got in class. When you're done, come back to this video. Okay, so now let's talk about bias and variability. So bias is a term that we use when we're referring to the mean, and what bias is the difference between the center of the sampling distribution and the true center of the population. So we say that a statistic is considered unbiased when the mean of its sampling distribution is equal to the true mean of the population. So if we go back to our simulation Okay, so here I ran the simulation with a sample size of 100. I took 50 samples, and here's my distribution. So the mean of this sampling distribution is equal to 0.50. Well, we know that the true proportion of orange candies in our simulation is equal to 0.5. So since these are relatively equal, we would say that this statistic is unbiased because the mean of our sampling distribution is equal to the true proportion of orange candies. So that's what it means to be unbiased. We use the term variability when we're referring to the standard deviation, okay? And the variability refers to the spread of the sampling distribution. So main idea here, as we saw in our sampling distributions activity, or what you should have seen in your sampling distribution activity, is that the larger random samples that we have, the lower the variability and the lower the bias, meaning that your mean of your sampling distribution should be closer to the true mean, and the variability should be much lower. So looking at comparing the standard deviations for the n equals 100 versus the n equals 50, the n equals 100, the standard deviation should have been smaller than n equals 50 because 100 is a larger sample than 50, or 25, excuse me. Okay, so here's kind of a visual to represent bias and variability. So imagine you have an archer shooting many arrows at a target. 4 situations can occur, okay? So here's this first one. You would say that the archer is consistent but off target. So relating that to bias and variability, that means they have high bias because we're far away from the center. However, there's low variability because our arrows are all close together. B is a situation where we're all over the place. However, if we were to average, we kind of average towards the bullseye, but each result is far from the center. So this would be considered having high variability because there's lots of spread. However, it'd be low bias because it kind of averages to the center. Number 3, or C, this is where we have an archer who is consistently missing high and to the right, but they're not as consistent as part A. So not only are they far from the center, there's a lot of variability in their shots. So this case was an example of something with high bias because it's far off from the center, with high variability because our points are also, our arrows are all spread apart. And then lastly, D, this is ideal. This is low bias and low variability. Not only is the archer hitting the bullseye, they're hitting it consistently. So that's low bias because it's near the center, and low variability because the arrows are close together. So here's the same thing with dot plot. Low variability, low bias, points are close together and clustered around the true mean or true proportion. This would have low variability but high bias. Points are close together, however, it's all shifted away from the true center. This has high variability, low bias. If we asked to find the center of this distribution, it would be close to where the true value is. However, it's spread out, which means there's high variability. And then lastly, the worst situation where we have high variability, high bias, points are spread apart, the center of your distribution is far off from the center of the true mean or the true proportion. All right, so you should only write the highlighted part down. So the central limit theorem, so if you notice when we did our distributions here, when you first started out, so if I reset this, right, and maybe we take one sample at a time, as we draw more and more samples, your distribution becomes more and more normal, right? If we do 5 samples at a time, the distribution is closer and closer to a normal distribution. So let me increase this and do 10 samples. Right, so no matter what our parent population looks like, if we keep taking samples of a certain size and make a sampling distribution, that distribution is going to be approximately normal. So for any population, when n is large enough, the sampling distribution is approximately normal, no matter the shape of the parent distribution. So the larger our sample, so if instead we took samples of 1,000, it would look even more normal. Okay, if we took samples of 5, it's going to be kind of all over the place. But if our sample size is large enough, the distribution is going to be approximately normal, no matter the shape of the parent distribution. All right, so that's it for the notes. So you do have homework for this lesson. So go on Canvas, homework 7-1, which is due tomorrow by the end of class. If you have any questions from this particular lesson, remember I will address any questions tomorrow in class, but we will continue this unit tomorrow.